Alright guys, thanks for tuning into my video. The focus of this chapter is going to be triple integrals. And triple integrals are heavily related to the material we just finished with double integrals. Remember that Unit 9 was all about, first of all, double integrals, but second of all, transforming our double integrals in xy space to perhaps variable spaces that are more conducive to performing your calculation. So we did a lot of things where we had an xy space integral. It would have been too ugly to compute in xy space, at least by hand. And so we switched over to some more favorable uv space. It's a change of coordinates or a change of variables. So the variable x gets changed out for some transformation x of uv. The variable y gets changed out for some transformation y of uv, some function y of uv. And then, of course, you need an area conversion factor that allows you to change from an xy space integral over to a uv integral, accounting for the fact that our map is probably not an area-preserving map. So that was kind of Lesson 9 in a nutshell. Lesson 10 will have that same material, but the other thing we're going to talk about is just how to interpret the triple integral notation, because it can seem kind of abstract at first. It's really not as bad as it sounds, though. So let me give you your first kind of framework or concrete way of understanding this very abstract-looking notation of a triple integral. So first things first. If you wanted to find the length of an interval on just the real line, imagine you had the x-axis or something, and you're trying to find the length of the interval from some point A to some point B. Well, you could actually use calculus to do this. It would be kind of pointless, and I realize it's just b minus a, but you could do the single integral over the interval with respect to x, and that would give you the length of this interval, b minus a. We did the same trick with double integrals. If we wanted to find the area of a region, we realized we could do the double integral of 1 dA over our region, and that gave you the area of the region. Well, guess what? It kind of just continues with that pattern. So if we wanted to find the volume of a region, we could do the triple integral of 1 dV over our three-dimensional region R. I have a quick little example here. It's not too exciting. I've got a cube. You can see it's a cube of side length 2. Each of these intervals has a length of 2. So, of course, one way that you could find this volume is volume of a cube is side cubed. Each side is 2 units long. 2 cubed is 8. And, of course, you've got the volume that way. Of course, we're trying to develop calculus techniques here. So to use a calculus technique to do this problem, the setup's not too exciting. Remember that these integrals are evaluated inside out. So we could see our dx integral, x varies from -1 to 1. Our dy integral, y varies from 0 to 2. And our dz integral, z varies from 1 to 3. And then to evaluate the integral, remember we work inside out, so the antiderivative of 1 with respect to x is x. Plug in 1, plug in -1, subtract the 2. And you get a number there, and then we're going to do the same thing with respect to y. That's where this 2y comes from. Then plug in y equals 2 and y equals 0, subtract them, and then do the same thing, take the antiderivative with respect to z, and you get to 8 eventually. It was a lot of work to calculate that the cube has a volume of 8, so it's kind of pointless. The thing to remember, though, is most of the time we're not going to be using triple integrals just to do a straight-up volume calculation that you could have done using a geometry formula. We're going to try to do more interesting calculations, and we're going to build up to that very quickly. All right, so let's spice this up a little bit. We'll do another volume problem for now. And then we'll talk about another interpretation of triple integrals that goes beyond volume when you start messing with the integrand and having an integrand other than 1. But here's a slightly more complicated geometry problem. So I want to find the volume of the region that's above the xy plane, above the xz plane, and above the yz plane, but below the plane given by this equation, x plus y plus 4z equals 8. The region looks like this little guy right here. It's a little pyramid-looking thing. And of course there's geometry formulas you can use to find the volume of that region. We'll use that to check our work, but that's not the point of these problems. They'll get more complicated than basic geometry formulas very soon. Alright, but long story short, if we have x plus y plus 4z is equal to 8, well, I need to set up limits of integration on a triple integral. And just like we were, doing double integrals over a region where, if you're doing a double integral over some region in xy space, you had a top bounding curve and you had a bottom bounding curve. And that's kind of how, you had your top function of x, your bottom function, your bottom function is a function of x. And then your x would go from -1, or whatever it is. I don't know what these numbers are. I'm making this up. 1 to 5, let's say. Something to that effect, right? So we had a top bounding curve and a bottom bounding curve when we were doing double integrals. We do the exact same thing when we're talking triple integrals here, but now we need a top bounding surface and a bottom bounding surface. And that's what I did. By taking x plus y plus 4z equals 8 and solving for z, this is my top bounding surface. And then you could see, because the bottom of this region is the xy plane, that's given by the equation z equals 0. So I kind of have my innermost integral of my triple integral figured out. Now you need to figure out your second innermost integral. By the way, this is going to be a dz, dy, dx triple integral. So I figured out my integral with respect to z. I've got my z top and my z bottom here. Next I need to do my dy integral. And what you want to imagine is this is basically just looking at, I guess, pretend you have a projection of this region. Kind of pretend you're looking down on it from above. So imagine looking down upon this little pyramid thing, looking straight down on it. That projection of that region on the xy plane would look like this triangle that we have here. And the way to figure it out, really what I'm doing is I'm finding the intersection between the top bounding plane, z equals 8 minus x minus y all over 4, and the bottom bounding plane, z equals 0. And practically speaking, the best way to find the intersection between these two planes is to plug one into the other. So I have z equals 0. I'm going to take this z value of 0, plug it into this equation. So I have 0 equals 8 minus x minus y over 4. And I'm going to solve this equation for y so that I have a top curve and a bottom curve. This is just like a double integral now. So if I solve the equation 0 equals 8 minus x minus y over 4, of course when you go through that process, you end up getting y equals 8 minus x. So that's your top bounding curve now for your middle integral. And then you can see right here, this is pretty straightforward. Your bottom bounding curve is y equals 0. So that's my second integral in my triple integral. And then you can see in the picture here, x goes from 0 to 8. So your dx integral is going to go from 0 to 8. So here's my setup. This takes a little while to wrap your mind around at first, but a little bit of practice, you guys are going to be just fine. We'll do a couple more problems with this as well. All right, and then to be honest, the calculation of a triple integral is pretty much the same thing as a double integral or a single integral. Once you can do a double integral, a triple integral or even a quadruple integral is very, very doable. In fact, you guys are going to see quadruple, quintuple integrals in later chapters, mostly as extension problems, but they're kind of fun to do. They look really fancy, right? You look like you're doing some pretty crazy math if you see things like this. But yeah, that's not yet. That's next chapter. All right, so I've got this triple integral here. Z goes from 0 to 8 minus x minus y over 4. Remember, this is just a top surface and a bottom surface, an equation for a top surface, an equation for a bottom surface. dy, 8 minus x on the top, 0 on the bottom. It's a top curve and a bottom curve when we find the intersection between these two surfaces. And then my dx, I'm just going from left to right, x going from 0 to 8. So you find the antiderivative of 1 with respect to z, and you plug in your 8 minus x minus y over 4 and your 0. here's my 8 minus x minus y, and I took that 1/4 out, that constant of 1/4, just because it was kind of in the way. Then you find the antiderivative of 8 minus x minus y with respect to z, plug in y equals 8 minus x, and plug in y equals 0, subtract the two. This is just fundamental theorem of calculus, folks. Then we also take our next antiderivative, plug in 8 and 0. So we're pretty much there. This is just the step where I'm plugging in y equals 8 minus x. You can see that happen here, and here, and here. And I'm not going to fill in the rest of it. You guys are experts at this point with single integrals. You get 64/3. And by the way, that 64/3 is the volume of this pyramid little region here. And of course, you guys all know a geometry formula that would do this problem a lot faster. 1/3 area of the base times the height. The area of the base is 32. You just find the area of this triangular base here. The height is, well, you could see it right here, 2 units. So you could plug into an old-fashioned geometry formula, get the same 64/3. The thing to remember, though, is these are not all volume calculations. We're going to do much more interesting things. For example, triple integrating a function that depends upon x and y and z. And once you do that, it's no longer a volume calculation. It's a triple integral that has an integrand. And I'll give you guys a framework for trying to understand something that is much more abstract, like this, a triple integral with an integrand that's not just one. By the way, you could repeat example 2 by computing, before I did a dz, dy, dx integral, and in my opinion, that's usually the easiest order to go in. I really like going dz, then dy, then dx, because for z, we could think of a top surface and a bottom surface. It's kind of nice thinking about z as your surface, your top surface and your bottom surface. Your dy, your top curve and your bottom curve. And then for dx, integrate from left to right, just along the x-axis. You usually think of z as depth and y as height and x just as left-right movement. So I think that's usually the easiest. However, you guys know how this is going to go. On the quiz and on the U of I midterm, they might ask you to change around the order of integration, and they might specify, hey, we want you to do this triple integral, dy first, then dx, then dz. It's just a little bit of algebra, though. It's nothing too crazy. So it's the same sort of setup. You take your x plus y plus 4z equals 8, and all you do now is solve y equals 8 minus x minus 4z. And you have a y top surface, 8 minus x minus 4z, and a y bottom surface, y equals 0. So your innermost integral is all set. Now you need to look at the intersection between your top bounding surface that's solved for y and your bottom bounding surface that's again solved for y. So you find the intersection between 8 minus x minus 4z and y equals 0. Well, that's just going to be 0 equals 8 minus x minus 4z. And if you solve this now for, let's see, my next integral is a dx integral. So I'm going to solve for x. So I have x equals 8 minus 4z. That's our x top curve. And then x bottom, you could just see that's right here along the bottom, z equals, or x equals 0, sorry, this horizontal line on the xz plane. You can see how this kind of turns things on its head. It's not the worst thing in the world, but now we're finding the intersection between a top bounding surface and a bottom bounding surface. That intersection happens in the xz plane. So, it kind of makes it a little bit more abstract, but it's nothing too crazy. We're just changing variables around here, changing the order in which we're doing the problem. And now you can see that z, for your outermost integral, goes from 0 to 2. So x before was going from 0 to 8 for our first version of this triple integral. Now z just goes from 0 to 2, no big deal. And there's your setup. And if you did it right, you should get the same answer. You're going to get 64/3. I'll leave that as an exercise for you guys to do on your own. All right, so a lot of this chapter is all about analogy and just kind of building upon the material that you've already worked with and already mastered and the sorts of examples that you've already dealt with. Example 4 is no different. This is, if you remember those parallelogram problems that we did in lesson 9, all you needed was to solve a system to get your change of variables. You needed to find your Jacobian determinant, and once you were able to do that, you were able to do your double integral with a parallelogram-shaped region without too much difficulty. Guess what? Example 4 is the same sort of deal. So I'm going to pick a clever change of variables. Now instead of a parallelogram, I have a parallel piped. Now instead of a parallelogram that's bounded by 4 straight lines, my parallel piped has, 1, 2, 3, 4, 5, 6 different planes that bound it. But, very similar to a parallelogram. I'm going to pick a very clever change of variables the same way that we were doing last chapter. So if you look here, you have your z equals 3x and your z equals 3x plus 2. You could use that to say, hey, maybe u should equal z minus 3x. Let's see if if u equals z minus 3x. Looks like u is going to go from 0, there's a plus 0 on this, to 2. Similarly, I have this y equals x and y equals x plus 4. These are planes, not lines. I know that looks like an equation for a line, but it's a plane. I'm going to do v equals y minus x, and it looks like v goes from 0 to 4, just like you can see in the green box here. And then similarly, w is going to equal y plus 2x. You're going to do the same sort of thing for your change of variables, and you can see that w goes from 0 to 3. All right, this integral is a lot more manageable as a u-v-w space integral. The only thing we have to be careful with is, again, just like with double integrals, you couldn't just change coordinate spaces. You couldn't just map from xy space to uv space and do the double integral there without accounting for the fact that your mapping is non-area preserving. Well, our mapping that we're coming up with here is not volume conserving. And so, since it's a non-volume conserving map, you need to adjust for that. This fancy looking thing here is called the volume conversion factor. Might look scary. It's the same formula. It's you could either call it the Jacobian determinant, it's actually the absolute value of the Jacobian determinant, or you can call it the volume conversion factor. Either way, it's still the determinant of a matrix. It's just now instead of a 2 by 2 matrix, it's going to be a 3 by 3 matrix. No big deal. So this is the triple integral I need to compute. What I've done is I've mapped from an XYZ space where my region was a parallel piped to a UVW space where my region is a rectangular prism. So this is a nice little, it's a box, right? This thing, instead of being a rectangle in XY space, instead of being a rectangle in UV space, this thing is a rectangular prism or a box in UVW space. Nice looking limits of integration, constant limits of integration. And the only thing that's complicated is living here inside of the integrand, and I need to figure out what that volume conversion factor is. Here's the formula for the volume conversion factor. Make sure you know it. You know how this is going to work. This is going to appear on the quiz. This is how it goes. I'm going to have you guys regurgitate that formula. But it's nothing too crazy. It's the same formula that you guys knew, and I just added an extra letter of the alphabet. dx, dy, now dz, du, dv, now dw. So after y comes z, after v comes w. So your volume conversion factor is going to work the exact same way. I would recommend that you practice taking determinants of 3 by 3 matrices, because if you don't, well, it won't end well, right? But you'll get lots of practice on the lit sheet and stuff doing that. So yeah, here's my big summary slide. This is what I would leave up on the board for a period of time to make sure you got it down in your notes. This is a great time to pause the video and make sure you get, this is the big formula from this chapter. The only thing that I haven't done yet is add in an integrand in my triple integral. This is just a volume calculation. But still, this is how to do an XYZ volume calculation in a more favorable coordinate space, using some transformation, x of UVW, y of UVW, z of UVW. And usually when I memorize the volume conversion factor formula, I like this version on the right here. Kind of like it better than this T1, T2, T3 for the 3 coordinates of the transformation. And then remember all this gradient stuff that we were talking about before is here. So we have our first column in this, our first column that you see inside of this 3 by 3 determinant is the gradient of x as a function of u, v, w. Same thing here. You've got the gradient of y as a function of u, v, w, and the gradient of z as a function of u and v and w. That's a great way to remember it. Just like before, volume conversion factor needs to stay positive. Volume can't be positive, so when we're making that adjustment, you take the absolute value of the volume conversion factor in your triple integrals. All right, so let's finish up this problem. So here is my change of variables from before. Remember that this is u as a function of x, y, z, v as a function of x, y, z, w as a function of x, y, z. We need to solve a system of equations to solve for x and y and z. I need x as a function of u, v, w, likewise for y, likewise for z. It's just a system of equations that you can solve with elimination and substitution, though. I'm not going to show you guys how to do that because you're experts with that sort of stuff by now. You do need to know how to do that by hand, though, on the quiz and the midterm. So x equals w minus v over 3, y equals 2v plus w over 3, z equals u plus w minus v. You can make Mathematica do this pretty easily as well. To compute your Jacobian determinant, you just follow the same sort of procedure as before. I'm not going to do all of these entries, but remember that this first column is the gradient of x as a function of u, v, and w. So if you look at the x-coordinate of your transformation, this first entry is the partial derivative of w minus v over 3 with respect to u. Well, there's no u's in this thing. So the partial derivative of w minus v over 3 with respect to u, of course, is 0. Then the next variable is v. So the partial derivative of w minus v over 3 with respect to v is negative 1/3. There's your negative 1/3. And then, again, your w minus v over 3, when you take its partial derivative with respect to w, okay, the derivative of w is 1. The derivative of negative v with respect to w is 0. So I have 1 over 3. Oh, 1/3. There it is. And you could fill in your entire volume conversion factor that way. You got to know how to take a 3 by 3 determinant. This one has a shortcut in it, though. We just got kind of lucky here. If you take a look, this 3 by 3 determinant kind of has a little handle here, right? There's these zeros make this a much easier determinant to take. So we really only care about this 1 times the minor of this small 2 by 2. So working this one out by hand is not a lot of effort. You just get negative 1/3. We're going to use positive 1/3 in our calculation, though, because you don't want to use a negative volume conversion factor inside of your triple integral. So the calculation we have to do is just this triple integral of 1/3 du, dv, dw, where u goes from 0 to 2, v goes from 0 to 4, and w goes from 0 to 3. I'm not going to show you the work for that. You guys are experts there. You know it's going to be 8. All right, so that parallel pipette stuff, pretty much the same as the parallelogram shortcuts that you learned in lesson number 9. And by the way, if you are on math team, you might be interested in this formula. It's called the triple product, and it's a nice little shortcut for finding the volume of a parallel pipette without having to use calculus. So on a math team contest, you find the 3 vectors that define your parallel pipette. So find that basically you'd have to know the intersections of those planes, which you could do pretty easily, or in a math team contest would be kind of given to you. Anyway, so find the 3 vectors that generate your parallel pipette. Do the cross product of the first 2, call those x and y, take their cross product. Then dot product with the third, and call that third vector z. And that will be the volume of your parallel pipette as well. The thing to remember, though, is we're not doing just volume calculations during this chapter. I know the first few examples I've done are volume calculations, but there are other kinds of calculations we can do that are more complicated than just simple formulas from geometry or formulas that you might know from like competition math team stuff. Okay, one concept that I should remind you of, and by the way, you can probably guess that this is here to prepare you for the try-it problems, because you can see a Mathematica looking plot here. But remember that if you can parameterize a region, then you could double integrate over it. That was what we learned in lesson 9. If you can parameterize a region in XY space, then really that parameterization in XY space was a mapping between a UV space rectangle and your XY space ugly region, whatever it is. Well, that concept holds true in higher dimensions as well. So if I can parameterize a region in 3 dimensions, then that's actually just a mapping between a UVW space box or a UVW space rectangular prism and my weird looking region in XYZ space. And if you could parameterize that 3-dimensional region, you can integrate over it. So that's what I've got here. I've got the skin of a football looking region right here. It's not filled in. You can see it only has 2 parameters here. 2 parameters means a surface, so it's a non-filled in football shape. So if I fill in the football, then I've got a parameterization of this filled in region, and then I can get a mapping between a filled in box or a filled in rectangular prism and my filled in football, and I can triple integrate over it really easily. So here's how you fill it in. All I did was throw an r into this equation, and I let r vary from 0 to 1. Another change to notice here, this is a function of r and s and t now, rather than just a function of s and t. You'll have to make those changes in Mathematica as well. When when you're triple integrating, you'd have to rename your function if you were to use the function name inside of any integrals or anything like that. So just be kind of careful. I will say Mathematica can't plot. You can't use parametric plot 3D on a region that has 3 parameters, so you won't be able to plot this thing on the right-hand side. You'll only be able to plot the open skin. You do need to know how to fill in an empty skin, though. So if you have like the pig skin of a football and you need to fill that football with volume, you need to know where to put that R. It takes a little bit of practice to figure it out. You guys are going to be fine, though. The more practice, the better. The way that I kind of thought about this 0, 0, 4S, that's kind of like the central spine of this football. So I imagine that just kind of carrying me upwards on this football shape. And then this latter part, those are just kind of concentric circles. And so I imagined that the central spine of the curve, 0, 0, 4S, was carrying circles up through this shape. And they were not filled in circles originally, right? This is the radius of the circles. There's the parameterization for your circles. So empty circles of varying radii. To fill them in, to make them into disks, I need an R from 0 to 1 to fill in each of these circles and make them into disks, and then that will accumulate, our volume. Yeah, the more practice, the better. You guys will be great at that soon, though. So here's my change of variables. The parameterization is your change of variables. Remember, if you can parameterize a region, you're going to be able to triple integrate over it. By the way, 0 plus r times 4 minus s squared times cosine of t, that's your x. Basically, I'm taking the x coordinate of each portion of that equation. So that's your x of rst. I'll show you how to do your y of rst as well. It's the same thing, but 0 plus r times 4 minus s squared times sine of t. You can see that there. And then the only z coordinate that we have in the above parameterization is 4s. There it is. So that's our x of rst, y of rst, and z of rst. If we're going to map between coordinate spaces, though, if we're moving to an rst coordinate space where we have now a rectangular prism or a box, you need a volume conversion factor to adjust for that change. You can see it right here. By the way, look at how the bounds for our parameterization are also the limits of integration. So s was going from 0 to 2. That was given. That was a given piece of information. You could see how your ds integral goes from 0 to 2. Our r that we came up with that was going from 0 to 1, our dr integral is going from 0 to 1, and your t, your parameter t that we had going from 0 to 2 pi, you can see right here 0 and 2 pi for our dt integral. So you get the limits of integration from your parameterization. Anyway, so the only crazy thing left in this integral is figuring out our volume conversion factor. And what I'll tell you, or at least the absolute value of our volume conversion factor, you don't want to work that out by hand. It would not be fun. So have Mathematica do it. Just don't forget to take the absolute value of the absolute value of this thing when you take your triple integral, because we don't know when that's positive or negative, very easily at least. So this is a computer calculation. Have the computer do this for us. The volume of that football-shaped region is 2048 pi over 15. And you should just pause for a second, and not literally pause the video unless you need to, but just sit back for a second and think about how amazing it is. If I gave you guys that region, that three-dimensional region, back in your honors geometry class, back in 8th or 9th grade or whatever, and I said, find the volume of this football-shaped region, you guys would have just kind of laughed at me, because it couldn't be done using the math that you guys knew at that time. Maybe you could estimate it in some various ways. But now you have the calculus tools to find this exact volume. I will say there is a trick for finding that volume using solids of revolution that you guys learned in Calc BC. So this particular region, you could find its volume using last year's calculus. But if you looked at that calculus close enough, you'd find out that actually it's mathematically equivalent to what we just did. And this setup, I would say, is a much more elegant setup than using a solid of revolution. Here is, by the way, if you're curious, here is how you would do this using solids of revolution. You could look into it if you want to. I'm not going to explain where everything came from, but you can kind of work it out and verify that that's the correct answer if you're interested in doing so. So 2048 pi over 15, definitely the right answer here. All right, so we got to move beyond volume calculations, because volume calculations, we already have a whole ton of tools out there, a whole bunch of tools for handling volume calculations. You don't really need triple integrals just for volume. We were doing just fine with double integrals. However, if I throw an extra wrench in the works here, if I change my integrand just from the number 1 to a function of f of x, y, z, a function that depends on x and y and z, and I triple integrate that I do need some theory of triple integrals to handle. Here's the problem. We can't call this a volume calculation anymore. This is no longer a volume calculation. And that's because f of x, y, z lives in 4 dimensions. You can't picture f of x. This is essentially w equals f of x, y, z. That's a coordinate space that has 4 mutually perpendicular axes. I can't even picture 4 mutually perpendicular axes because that's in 4 dimensions. So instead of thinking of this as a hypervolume calculation, by the way, it is a hypervolume calculation. That's hard to wrap your mind around. I have a much more concrete way of looking at this. And so I'm going to come up with an example that I'm going to keep on referring back to through this entire chapter to give you a little bit of intuition. So here's what I want you to do, and literally do this throughout the entire chapter. Every time you see an f of x, y, z inside of a triple integral, think about it as a density function. Pretend you are in 3-dimensional space, and you have some 3-dimensional region R, and inside of that region R, your region is of varying density. Some parts are heavier, some parts are lighter. Some parts maybe are made out of lead, other parts are maybe made out of styrofoam or something like that. So a region of varying density. And what you can do is if you triple integrate the density function over your region R, what you accumulate is the mass of the region. So that's the best way to think about a triple integral. And it comes up in all sorts of other scientific and engineering contexts. But to make it concrete and to make it not too difficult to wrap your mind around, whenever you see a triple integral of an f of x, y, z dv, think of f of x, y, z being a density function for a region of varying density. And when you triple integrate the density over the region R, the 3-dimensional region R, what you accumulate is the mass of your object. So here's an example. F of x, y, z equals y squared times y, or x squared times y to the 4th grams per cubic centimeter, let's say. So this expression right here represents the mass of your region. And this region has a mass of 128/15 grams. Even when you're working with problems that don't have this context, or are not talking about physics or centroids or centers of mass or any of that sort of stuff, still try to think about the triple integral of f of x, y, z as a mass calculation. you're triple integrating the density over a region, getting the mass. It'll make a very abstract idea very concrete for you, and you'll have some good intuition. This is my little summary slide right here, so feel free to pause this video right now if you want to write down any of this stuff in your notes. You know how this goes. Expect to write this on the quiz, and expect to need to regurgitate the Jacobian determinant on the quiz. That's pretty much just how it goes. I'm going to have to give you a lot of space on the quiz though, because that's going to take a long ways to write. But you're getting points just for knowing the formulas in the class. So, all right, and then just if you ever need to think about this again, look at this slide here, and it has a reminder that you want to take this abstract idea of the triple integral of a function. Don't think about it as hypervolume. Don't think about it as a function living in a four-dimensional coordinate space. Just think of this in three-dimensional space. Think of a region in three-dimensional space of varying density, and when you triple integrate it, you get the mass. I know I'm being repetitive here, but honestly, it'll make this a lot easier for you. And here's another example. I'm taking the same parallel pipette we had before, so I'm not really redoing all of this work over again. I'm gonna reuse what I already had. So I'm gonna do the triple integral of 9y dx dy dz over this parallel pipette region, this three-dimensional parallel pipette that I was already working with. So all of this is just reused from example 4. My change of coordinates, my limits of integration, my change of coordinates now solved for x and y and z, and my Jacobian determinant, the absolute value of which is 1/3. Reusing that over again. So this triple integral in xyz space, it's a triple integral over a parallel pipette region. We're going to pretend that this parallel pipette is of non-constant density. It's of varying density. And so when we triple integrate that density function, we're going to get the mass of this parallel pipette. Well, we're going to move to a more favorable coordinate system. We're going to move to UVW space, where this parallel pipette becomes a rectangular prism, or just a box. And look, the only exciting thing here is this y gets replaced with y of UVW, but I have the equation for y of UVW. We actually already found that before. And then my volume conversion factor has an absolute value of 1/3 as well. I'm not going to really show you the work on that. I'm going to leave you guys to do this calculation. But we took an ugly calculation and we made it into a pretty nice one, because the limits of integration are all constants. So we kind of achieved our goal here. So there it is, simplified, and the final answer when you do the math is 132. This would be a perfectly appropriate quiz question. This is the sort of thing that would make sense to ask on the quiz. And finally, last but not least, I'm just going to do a very traditional looking triple integral. If you open any Calc 3 textbook, any multivariable calculus textbook, this is the sort of triple integral calculation that you would expect to see. I just want to make sure, if you guys go on to continue studying math in college, if you do anything technical in a STEM field, engineering, physics, all that sort of stuff, this is the sort of triple integral you would see in a later class that's using calculus. And also, I guess midterm quiz, again, this would be appropriate. So set up, but do not compute, the triple integral of 2y dx dy dz. Notice that when it's a dx dy dz integral, you can kind of switch things around to the order that you think is more appropriate. So I'm probably going to make this a dz dy dx triple integral, just because I prefer thinking about a top surface and a bottom surface, a top bounding curve and a bottom bounding curve, and then x, my outermost variable, going from left to right. So don't feel locked in to an order of integration unless you're specifically told that you have to leave it in the order that was given to you. So my first step is I made this a dz dy dx integral. Z top is the paraboloid, z equals 9 minus x squared minus y squared. That's the paraboloid that's up here, solved for z. And then the plane on the bottom here, the xy plane, also known as z equals 0, is my bottom bounding surface. So I have my top bounding surface, my bottom bounding surface. Those are my limits of integration for my innermost integral, my dz integral. So Got my dz integral sorted out. Now you need to find the intersection between your top bounding surface and your bottom bounding surface. Z equals 9 minus x squared minus y squared is your top bounding surface. Z equals 0 is your bottom bounding surface. Find the intersection between those two surfaces. You just set them equal to each other. You put 0 in for z in this equation here. You have 0 equals 9 minus x squared minus y squared. You end up getting the circle x squared plus y squared is equal to 9. So I have my y top of y equals 9, y equals the square root of 9 minus x squared. I've got my bottom bounding curve from the intersection of those two surfaces. The bottom bounding curve from that intersection is y equals negative square root of 9 minus x squared. And you can already see that x is going to go from negative 3 to positive 3. So you can pretty much see your setup here. And let me erase all of the ink on this slide just so it's not too crazy on here. And here's my setup. Set up but do not compute this triple integral. Here it is. And you should be good to go. Now what I will say is the reason it says set up but do not compute is this would be a really, really ugly integral to crunch the numbers on. This would be a very appropriate integral to do a change of coordinates, a change of variables on. However, we're not quite ready to do that change of coordinates yet. Next chapter we will be. There is a mapping to a UVW space that makes a lot of sense using something called cylindrical coordinates. We'll look at cylindrical coordinates a little bit this chapter. They're previewed a little bit in the triad problems, but then mostly they're covered next chapter. So for now we're leaving this as a setup but do not compute. Later on we'll actually be able to crunch the numbers because we're going to move from an XYZ coordinate space where this is a really pretty ugly triple integral to a coordinate space where it works out pretty nicely. Alright, well, one other thing I guess I should remind you of. I know that this is super repetitive and I apologize for that, but remember that you should try to think of this triple integral as computing the mass of this filled in paraboloid sort of region. The varying mass, the density at any given point is given by the density equation f of x, y, z equals 2y. So that's my density equation. And if I triple integrate the density over my x, y, z region, I get the mass of that filled in region. So that's how you should interpret this thing. And if you're curious about what that quote-unquote mass works out to, it's not a literal mass, but that's where we're thinking of it as a mass calculation. You can run this through Mathematica, and you could see what the computer gives you. And then look forward to next chapter when we'll actually crunch the numbers. All right, guys, thanks so much for tuning in, and good luck on the triad problems. Keep an eye on those deadlines. All of the dates that you need are on Schoology.